friends, welcome to the class 11th. Okay, in the last class we had learned regarding the cycloheptatriene. Okay, which is we ended with cycloheptatriene. Okay, and we had learned regarding the tropylium. That is very much important. They will ask in the examination. Tropylium cation, which was 6 electron species. Okay, and today we'll go for cyclooctatetraene and cyclobutadiene. This already we have learned here. Okay, no problem. So this we will learn, and this small part we will touch it today. So what about this cyclooctatetraene? Okay, so this is if you see it according to Haeckel's rule, that is 4n plus 2 rule. Okay, pi electrons. So both the cyclobutadiene and cyclooctatetraene are non-aromatic in nature. This thing you have to keep in the mind. Non-aromatic and it contains the alternating bond length. Okay, and has a tub type shape. This cyclooctatetraene. Okay, you know that. So like this somewhat 1, 2, 3, 4, 5. Okay, then 6, 7 and 8 like this. Okay, so this is what we are going to see here and here like this. So tub shape. So this cyclooctatetraene is having tub shape. This is also called as COT, cyclooctatetraene, and this is non-planar molecule. So you can see here this is a non-planar molecule, and if you see this the reaction, but this non-planar molecule it becomes now planar. This is very much important. This becomes planar if you treat this. Okay, if you treat this with some of the active metals. So if you treat this with some of the active metal, okay, so what happens, it produces cyclooctatetraenide anion. So it will produce a cyclotetradenide anion, that is -2. This is very much important. Like for example, if you treat this with potassium plus if we take this cyclooctatetraene cot, so you are going to get 2K plus COT minus 2, or I can write C8H8 minus 2, C8H8 minus 2. This is called cot minus 2 cation. Okay, cyclooctatetraenide anion. So this is called as cyclooctatetraenide anion. Minus 2 is there, no? So this is what? Okay, cot minus 2. Now what is the fascinating of this compound is this aromatic this is aromatic in nature. Okay, so this like cyclopentadiene anion we have studied for this cyclop anion. So this COT minus 2 is also aromatic in nature. This is what? Okay, this also is aromatic in nature, and but how many pi electrons it is having? It is having 2, 3, 4, 5, 6, 7, 8 pi electrons. So it is having 8 pi orbitals. Okay, and how many electrons it is having now? 8, 9, 10 electrons. Okay, so after getting this -2 charge, it will have 8, 10 electrons, but it how many pi orbitals is having? 8 pi orbitals. See, this is a very important here. 8 pi orbitals but 10 electrons. Okay, and when this is allowed to react now with tetra positive, when this condition in this condition, when it is allowed to react with tetra positive any of the cations like actinides. Okay, the tetra positive means uranium plus 4, plutonium plus 4. Okay, like this. Then neptunium plus 4, thorium plus 4, this way. So when you treat this with the salts of this, like uranium tetrachloride, when I treat this with this cot minus 2, that is your anion. Okay, so what I'm going to get? I'm going to get this compound, that is uranium with 2 molecules of the cyclooctatetraene anion. Okay, minus 2. So I can do it like this: 1, 2, 3, 4, 5, 6, 7, 8. Okay, so like this. So uranium here again 1, 2, 3, 4, 5, 6, 7, 8, like this. Okay, you can do it, and this is called uranosine. This is also metal ion, this one is called uranosine, where this is two eclipsed rings, you can see. Okay, and in between that uranium is there. Eclipsed means same side, like in ferrocene also if it is having like this, both same side, ferrocene Fe, and same side if you draw this like this, okay, so this is called eclipsed. This is called eclipsed. But if you see in opposite side the rings, like one I draw in this way, here iron is there, and another I draw in opposite way like this. So this is like this here like this, so it is called staggered. It is called as staggered. This is what you have to keep in the mind. Now in Uranosine you can see here, so it is in eclipse form, both same ring we can see here, so that's why. Now like this most of the lanthanides do, sometimes they are also going to form the similar complexes like Uranosine, where they are going to utilize the 4f orbitals, okay. So these lanthanides 4f orbitals instead of 5f. These actinides are using 5f orbitals to form this type of complexes, but lanthanides they are going to utilize the 4f orbitals here, okay. And now if you see this, they may ask this one, so they are going to form like this, lanthanide quad twice, okay, minus this type of complexes they are going to form. Now if you see this cyclobutadiene, now this is what about cyclooctatetraene, okay, that is C8. Now if you see the cyclobutadiene, in the previous classes we have learned regarding the cyclobutadiene much, and today we will not go into deep of the structure and bonding here. So we have learned that this is highly reactive, okay, this is highly reactive. So why this is highly reactive? So you know, non-aromatic first thing, and second thing you can see that okay, so this is having two unpaired electrons, and if you see the IR spectra of this cyclobutadiene, so at low temperature at 35 Kelvin, okay, it dimerizes. This all we have learned in the previous videos, okay. It dimerizes, and it is shown to be rectangular shape, okay. And with the IR help, with the IR help, it is known to be rectangular with alternating single and double bonds, okay. So this is what about the cyclobutadiene. In previous videos also we have learned here of this unreactivity. But when you treat this unreactive compound, like you take this compound, okay, so ClH, you substitute this like this, and when you treat this with complex CO9, you can take this, okay, like this, okay. So what will happen, being highly unstable form of this one, so it is going to form now this compound, this complex of the stable complex of your what do you say, carbon, like this. Now this is highly stable, this is highly stable, see, like this. So which was very not very reactive and very unstable molecule, this cyclobutadiene, so it can be made very stable here, okay, stable in the when it is going to form the complex formation. So this is what uh, about the cyclooctatetraene and the tetraene. So almost we have completed here this one part of this unit 1 here. So if I go for now compilation with some of the notes here, so most of the cyclopentadiene Cp2M, okay, so that what we represent having the carbon-carbon bond of a same length, okay, of having the same length, and usually all the rings are in the parallel way. So we have seen for ferrocene, usually all the ring are in a parallel way like this, okay. But in some cases what happens, some of the rings are tilted, that also we have learned, some of the rings are tilted, okay, so they are crossed here. And when this happens, you know, for example Cp2 rhenium, so big molecule, when you take because of lone pair of electrons or bulginess or hindrance, whatever we come across, so we can see that they are going to form the tilted molecules, like for example titanium, cyclopentadiene chloride, okay, or tantalum hydride. So these all things for is going to form the tilted, like this we can show like this, okay. So rhenium hydride like this, see here. So such type of tilted form also is going to form because of the steric hindrance or the lone pair of electrons, some is going to happen here, so to steric hindrances, okay. So like this, so titanium hydroxide or tantalum trihydride, so like such type of metallocines are also possible whenever we are going to see the steric hindrance, okay, or more number of rings or more number of ligands we are going to compare. So even triple decker also we have learned, triple decker type of metallocine, like nickelocine we have seen, okay, similar to that. In this way also we are going to observe, okay. So like this, okay. So we are going to see here cobalt. Then you can see here 1 2 3 4 5 6. This is very important here. Again cobalt. Again you can see here like this. So this type of molecule is also possible here. So this is neta 5, this is neta 6, and this is neta 5 again. So like this, okay, with having the cobalt here. Okay, so this type of triple deckers are also possible. Like in Nicolosin we have seen when there is more number of electrons than the 18 electron system, so the sharing will take place, and the electrons will share with the both the atoms, and this type of triple decker type of complexes can be seen here. And sometimes cyclopentane per metal is also observed in some of these complexes, organometallic cyclopentadienyl ring per metal atoms, like we have seen in this way. Okay, so best example, that is vanadium, then carbon monoxide is attached to this like this. Okay, so this compound is very red orange solid. So this is red orange solid. See here, this compound is very red orange solid and having the melting point of 138 degrees centigrade, MP 138 centigrade, but it is a air sensitive. This is air sensitive. That means in the air it becomes unstable, so very sensitive. So there should not be aerial this one, otherwise this will be degraded. Similarly, one more compound of the manganese, single atom and single cyclopentadienyl ring is there. Such also we can see in the metallocene in the organometallics. Okay, so this yellow solid, so this is a yellow solid here of manganese, and if you see the melting point, it comes around 173 somewhat, and also is a air sensitive. This also is a air sensitive. So one more compound you can see of iron, so like this iron. Okay, so again same thing here, so you can take it as iodide here, iron, two molecules carbonyl and one iodide, which is dark brown solid. So this compound is a dark brown solid. So okay, this compound, all three are solids. Okay, and having 119 degrees centigrade as a melting point. Okay, so this is what about some of the what do you say, metals organometallic complexes with single cyclopentadienyl ring is also possible. In some cases you can see there is a bridging between the metals, bridge between the metals. So you should know all the types of metallocines, and that's why this is very much important, you know. So this is what, so if you take that is molybdenum, so you take molybdenum in this way. So this molybdenum is been bonded with the 3 carbonyl here, and here also you can see molybdenum 3 carbonyl is going to bond like this. So such type of bonding is also can be existed during this formation of metallocines with different reaction intermediates here. Okay, so similarly one more we can show, so that is iron. Okay, so having this iron, and here we can show that like this. Okay, now here we can show the bridging is possible here like this with iron. So here carbon monoxide, here carbon monoxide like this. So this type of compound is also, this is red purple solid. So this compound is red purple, and this is purple red. This compound is purple red color, and if you see the melting point, this is 194 degrees centigrade but air stable. So this is air stable, but this manganese molybdenum compound is 215 degrees centigrade melting point, and it is air sensitive. This is air sensitive. See like this. So this compound is air sensitive, and this compound is air stable, and 194 degree temperature, and here 215 degree centigrade. Okay, temperature melting point, and this is air sensitive, and this is, so like this type of compounds organometallics can also be found. Now the next note to be noted is in the previous I had given you MOT, okay, molecular orbital diagram. So just I have taken here, so you can see here. So very simple I have taken from this. So in the last video I had given you very simple without giving the, what you say, the Mulliken symbols. But in this case, according to group theory, if you want to draw this here, so this is the metal. Okay, these are the orbitals of metal, 1 2 3 4 5, and this is a d orbital. So d orbitals, what will be there? A1g, E1g, E2g. So 2 3 4 5. Okay, so 5 orbitals are present: dxy, dyz, dzx, dx square minus y square, and dz square. So this is what 5 orbitals, and here A1g orbital of s will be there. S means single orbital, and p orbital A1u and E1u. Okay, A1u 3, so E1u and A2u. So like this, okay, so 2 plus 1 3 orbitals, p orbitals, so like this. These are the metal orbitals here. So first you generate this, okay, and this is important, you can keep in the mind. Similarly, you can see here 2 cyclopentadienyl, okay. So 2 means how many, this one then from here, if you consider the neutral elements, so neutral iron means what? If I take ferrocene of neutral iron, so 6, how many this will be there? Iron means scandium d6, 6 7 8, so 8 plus 10, so 18 electron, okay. That means these 2 cyclopentadiene in neutral form is going to donate 5 electron, that is 10. So you should have the 10 orbitals here. So see here 1 2 3 4 5 6 7 8 9 10. So 10 is generated here. So 10, how what you have to go for generate here? So first one is what? 2 orbitals here, a1g a2u, okay, a1g a2u, then e1g e1u, then e2g e2u. Very simple to remember, okay. Now these orbitals are ready of this 2 cyclopentadienyl. These orbitals are ready of the metal. Now what is there? Just you collaborate here. So prepare a molecular orbital diagram, that's all. So this is what I have given you in the last previous video. So simple, this I am giving with the terms here, as I said you in the last moment I will give you. So this is what I am giving. Now you join it here, a1u a2u, so you do it a1u a2u like this, and here you can join here. So a1u where it is there, you just see, you join it here, a1u a2u where is there, see a2u, so join it from a2u like this, okay. You know that, but important is this. Now see here, now what happens here? So first one you can take it as a, so this 2 is over. Now here e1u, okay, here it is, yeah. So this is e2g, okay. So e1u e1g, e1u of this one you can draw it here, e1g e1u e1g e1u, okay. Again you join it here, okay, where it is the same symmetry is there. So that is over. Now these 2 are over. So okay, these 2 orbitals we have made it here, this 2 and this 2 has come here. Now main comes of what? Metal orbitals. Now e1 e2g, so this is e2g 2 orbitals. What is that? Dx square minus y square dxy, okay, dx square minus y square dxy. So this is e2g, a1g here, so that is dz square. So from here a1g dz square, and e1g, that is your dxz dyz, dxz dyz e1g. So this I have taken a square here now. So now that represents the electrons to be filled here, okay. For example, ferrocene, as I said, d8 to d6 system, so 2 3 4 5 6. See here itself it gets filled here, ferrocene. That's why we say what? It's a diamagnetic in nature, okay. 6. Now if you go for cobalt, 7 something, it comes here, 1 unpaired electron like this, okay. Cobalt, nickel, another 1 electron, d8, so like this, 2 electrons, so 2 unpaired electron like this. You have to go fill and take out the all from vanadium, all 3D series. You can take out the MOT in the same way, and diamagnetic nature, and you can show this in the examination, very simple way. And other things, so when you are right here, so that is the anti-bonding now. So a1g a2u is there, you generate a1g star a2g star, like this is generation of the anti-bonding molecules. So e1g e2u e1u star e1g star, so like this. So whatever the bonding you are generating here, so same anti-bonding you have to generate here, and then simply you have to match the orbitals with wherever the same symmetry is there. So we have to match it, and some case you have to make it as a non-bonding, in some case you have to make it as a non-bonding, where there is no match will be there, so you make it as a non-bonding. But this is the important part, this is the important part, this is the important part, and this is what you have to keep in the mind, which type of orbitals is involved in the bonding. So with respect to this, so you can go for what you say, this one, MOT presentation for all the metallocene, okay. So whatever they ask in the ferrocene, mostly they will ask, so this is what you have to give for ferrocene, and whatever if they ask, you have to you can present it, okay. Now coming to structure and bonding in arenes, okay. This was about the MOT of previous this was cyclopentadienyl. Now if you go for arenes, similarly arenes, what will happen now? If I go for arenes, we show this arenes means what? Benzene ring, isn't it? 6 nita 6. So this is 1, so 1, this is 2, this is 3, this is 4, this is 5, and this is 6. That means 6 molecular orbitals we can generate it here. So one is psi1, then this is psi2, this is psi3, this is psi4, this is psi5, and this is psi6, okay. So psi1 means what? No nodes, so no nodes is there. Psi2 psi3, one single node, so this is having one nodes. Psi3 psi4 psi5, two nodes, okay. And last one is psi6, that is your 3 nodes. This you can generate, and you can draw it. Psi1, so very simple, you can draw it here like this, okay, like this. So 1 2 3 4 5 6 here. Psi1 means all the sides we can draw it here, same like this, all top, plus 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 like this. This is your psi 1. Okay, no nodes is there, and there is no center of symmetry also here, because you can see here top this is positive, this is negative. Okay, bottom it is negative, it is positive in this way. So there is no center of inversion also. It's having two electrons like this, and if you see the group this one, it is having A2U. Okay, this is having the symmetry of A2U. Now if you take next one psi 2 psi 3, so there you have to generate how many nodes now? Two nodes. This is psi 2, and I will write here psi 3. Okay, now how generation of nodes? So this is one generation I can do, and this is one generation I can do. Okay, now you can draw according to this. You can draw the orbitals now. So if I put like this, like this, like this, like one node I have to generate here. So if I go for now here top positive, so I should go for down negative. So top positive and down down negative. Okay, so this is what this is, or top positive and down negative negative. So like this is plus, this is plus, this is minus, this is minus. So this you can like this. So one node can be generated here. Similarly here also one node is generated, so you can do like this orbitals, and see here. So one node means what now here? So you can take all this as a top plus plus plus. You can take it as here minus, here top minus minus and minus, like this here. So this is minus 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 plus plus plus. So this is what psi 2 psi 3 we have generated here, and here energy is equal. If you see here, if you match the center of symmetry or inversion here, so here see, here top is positive, top is positive, negative, bottom is negative, bottom is negative, like this. That means center of symmetry is there. That's why if you see equal energy molecule psi 2 psi 3, and that's why the symbol is for this E1G. G means grade. That means center of inversion is there here, center of plane is there, axis is there. So E1G orbital will be there, and it's also having the 2 electron like this. Okay, that means 6 electrons, 2 3 4 5 6. This is about the psi 1 psi 2 psi 3. Similarly psi 4 and psi 5. Psi 4 psi 5, what is going to happen now here? So it is going to have how many nodes now? Two nodes. So one I will take here like this. So this is the two nodes I can take here. So you can draw it here like this one, and now you can put the nodes here. Now here if I take positive, I will take here down positive. Similarly if I take here down positive, I can take here top positive. So this is what about the psi 4. Similarly psi 5, if I take psi 5 now, same thing like this. Generate how many nodes? Again two nodes here. So this one nodes and this one node. So like this two nodes I can generate like here. Now simple way, again if you draw like this the orbitals here. So with two nodes, what will happen? So here one positive, here positive you can take. Here node is there, so down you take positive. Here also node is there, down you take positive. Okay, and here also you can take positive and positive like this. So this becomes your psi 5, this becomes psi 4, and this becomes psi 5. And here also problem is what? It is not matching. See here, top positive, the bottom is negative. So that's why this will have which Mulliken symbol? E2U. This you remember. Okay, so ungrade means there is no center of symmetry, plane of symmetry missing, so we take it as a E2U. So okay, this is what about this psi 4 psi 5. And last one is psi 6. Psi 6 means how many this one nodes will be there? There will be now 6 nodes, to 3 nodes, sorry, 1 2 and 3. So like this. Now you can draw the orbitals and generate the node according to nodes. You can generate the positive and negative. Simple. You can start with this top positive, down positive, top positive, down positive, top positive, down positive. So if you do this, it becomes 3 nodes, and this becomes your psi 6. Okay, and this psi 6 is totally out of plane, and it's not having 3 nodes means very, so that's why it will having B2G. Okay, so B2G type of Mulliken symbol here, that is not having any axis of symmetry, plane of symmetry, whatever it may be. So that's why it's a more haphazard way of this one, that we go some B2G like this. So like this, these are the different orbitals of the arene compounds. Okay, now if I go for the what you say mixing of this metal ions, so you have to see now you have to mix, and metal ions you have to join it. Okay, so A2G. So how many orbitals are there here? So so how many you see generates it will be generating here. So 2 E1G 2 are there. So here it is again here E2U 2, and here A1G, and here also B2G, because in arene complex we are adding again here what? To form the metallocene we are adding two compounds. This is one arene and this is one arene. Okay, and in between we are putting the metal now. So how many now here? So you have to double all this. That means how many molecular orbitals is going to happen now here? 1 2 E means 2 here. Okay, so 2, so 2 3 4 5 6 7 8 9 10. Is it right? So like this. So 10 molecular orbitals we have generated here. Like, so 2 2 2 you have to take it. So this all 2 you have to take, this one of 6 and another 6 you have to take. Okay, so totally 12. So 12 LGOs, ligand group orbitals, is generated here, 12. Okay, so this 6, another 6, this 6 we have generated, another 6, so like this 12. Okay, and now we have to see that which is going to overlap the metal ions. Usually if you see A to U, so all are like this, positive or negative. So if you take this, so best metal orbitals is your S orbital is commonly 4s orbital, which is having no like this is commonly is going to overlap with this, or best is dz square. Okay, so whatever it may be, so you take like this dz orbital and you overlap it here like this, and you take it opposite and you can overlap it here, and you are going to get the best overlap here. Okay, that is s or dz square, and sometime pz orbital also 4p or pz orbital also is going to overlap with this. Now if you go for this psi 2 and psi 3 orbitals, little bit one node is there here, one node means little bit this one. So that's why if you take px py, so pz is going to overlap here, so px py is going to overlap here. And if you see the d orbital 3d, that is d xz and yz orbital. Okay, d xz and yz orbital is going to nicely overlap with the suitable orbital orientation to this here. Okay, now if you go for psi 2 psi 3 psi 4 psi 5 here, so little bit two nodes is there here, single node is over. Now we are having the two nodes here, and so best here is dxy and dx square minus y square. So these two, dxy and dx square minus y square, is going to overlap, and this happens with the axis. If you take this x, y and z, so you have to see this axis in how the orbitals, and you have to join, there is a possibility you have to think like in the cyclopentadiene we learn. In that way you have to go and mix, and you have to see the symmetry. So psi 4 psi 5, so dxy and d x square minus y square is going to kindly overlap here, but in last one is non-bonding, so that is d psi 6. So no orbitals of metal is going to overlap with this, so this remains to be non-bonding, because three nodes are there, and it's not is going to, even psi 4 psi 5 also is psi 4 psi 5 also, one orbit may join with dxy or dx square minus y square. Okay, but one may not may come into the bonding here in this also. So that's why it's very difficult. But psi 1 psi 2 psi 3, okay, so they are going to be psi 4, so they are going to bond in the take part in the metal bonding interaction overlapping. Rest psi 5 psi 6, they are not going to be, they are remain to be unbonding, so non bonding. So like this. Okay, so this is what about the molecular orbital diagram of arenes. And this orbitals, you just take it, or you can draw the figures of these orbitals also in the examination and show the matching. This way we can do. Okay, so I think this is more than sufficient in this video. In the next video we'll go for the molecular orbital diagram of arenes, similar to what I have shown for ferrocene now, pentacyclopentadienyl. So that way we will go that, and if any points remained in this unit, first unit part, so I will touch that also, and that will complete your the first unit part of small part. And next will be some other ionic reactions pertaining to organometallic chemistry, oxidative insertion reaction, addition reaction. This all the second part of fluxional behavior of the molecule that we are going to learn. Okay, hope you understood this. Thank you.